Hello everyone and welcome to today's AZO Network webinar, which is brought to you by AZO Materials and our sponsors for today's event, Leica Microsystems. Today's webinar is titled Technical Cleanliness, New Demands of the Electromobility Sector, and a big thank you to the team at Leica for making this event possible today. Now, before we get started, we have a few points about how to get the most out of your experience. Firstly, the event is being recorded and we will, of course, share the on-demand link with you within the next 24 hours. So if you enjoy what you see or you've got a colleague or peer who might benefit from also seeing the content, then please consider sharing with them internally or via your social media channel of choice. If you happen to experience any technical difficulties, then they are normally resolved by refreshing your browser. But if this doesn't work, then send us a quick message using the Q&A box, which you can find on your right-hand side, and our team will get you back up and running as soon as possible. Now, today's webinar will run as two parts. In a moment, I'll hand over to Dr. Konstantin Kartashu, who will be hosting the event and the Q&A today, and we'll also be introducing our main speaker. Now, during the Q&A session, it is your chance to have any questions that come to mind during the event answered. So please use the Q&A box on the right-hand side, as I said, to send any questions in, and we'll get to as many as we can during the Q&A session after the presentation. Just a quick note that if you are watching this on demand, then you'll find the Q&A box on the bottom right of your screen, and you'll receive an answer to your question via email in due course. Finally, once today's webinar is over, we would really appreciate it if you could give us 2 minutes of your time to complete the end of webinar survey. This will appear once we are done today. Right, that's enough from me. I'm delighted to now hand over to Dr. Konstantin Kartashu to get things started. Konstantin, over to you.
Thank you, Danny. Hello and welcome also from my side. My name is Konstantin Kartashu and I am Advanced Workflow Manager for Industrial Applications at Leica Microsystems. As a provider of microscope systems, we like to help our customers to find the best solution for their applications. Today, however, it's a great pleasure for me to have with us Dr. Markus Rochowicz from the Fraunhofer Institute for Manufacturing, Engineering and Automation in Stuttgart, Germany. In the next 30 minutes, he will give us an insight into how the e-mobility transition and with that new upcoming demands are influencing technical cleanliness analysis. Markus is leading the Cleanliness technology group at the Fraunhofer Institute since almost 15 years, where he and his team played a major role in the development of the current VDA 19 and ISO 16232 standards. And with that, I'd like to directly hand over to Markus and wish you all an exciting webinar.
Thank you, Konstantin, for the kind introduction. Yes, before I start to tell you about the new demands of electromobility regarding technical cleanliness, I want to start with a review what happens in the last 20 or 30 years regarding particles, regarding technical cleanliness, about history and the technical demands. And from my point of view, it starts in 1993. As you can see on the picture on the left side, in this year, the anti-blockage braking systems go into large-scale production. That means nearly every car get an anti-blockage systems. And from the point of view from technical cleanliness or regarding the sensitivity to particles, we have the problem of blocking small valves inside the control unit of these anti-blockage systems, as you can see here on this drawing. So from that on, the companies producing these anti-blockage systems has to think about cleanliness in their production. That means the first cleanliness limits are established and the residual dirt tests are performed regularly at some companies, let me say 2, 3 or 4 companies producing these anti-blockage systems. In 1998, we have another big step regarding technical cleanliness, because in that time you can see the number of diesel engines or cars with diesel engines increasing dramatically. Let me say from 12 to 15% up to nearly 50% of all cars. And the reason for that was a big step in performance of the diesel engines due to a new generation of diesel direct injection systems that we have. And connected with that, we have dramatic increase of power densities, very small tolerances, very high pressures, up to 2,000, 3,000 bars that you can see at the graph here at the right top. Due to these very, very precise systems, the high injection pressures, the injection nozzles became very sensitive regarding particles that can block these nozzles. And in that time, the producers of these systems decide not just to solve these problems inside their companies, they wanted to buy clean parts from their supplier. That means the cleanliness limits are given to the entire supply chains. So a lot of companies, tens of companies, hundreds of companies have to deal with these aspect of technical cleanliness, cleaning their parts and checking cleanliness. And also in this time, around about 1998, the first fully automated particle counting microscopic systems are developed in a cooperation between Roche and Leica, and that was a very big step for laboratory people to make a precise and trustable measurement of particles. And with this progress in round about 2001, the first working group was established talking about a standard or a procedure, a standardized procedure to check technical cleanliness on laboratory level in, let me say, customer-supplier relationship. And before they start their discussions, because they want to talk about residual dirt, somebody raised his hand and say, okay, it's not possible to talk about residual dirt because that sounds negative. That sounds that we have problems with quality. Nobody wants to talk about quality problem. So the task was to think about a new word, a new terminology for residual dirt. And then somebody came up with the technical cleanliness. And everybody was happy with that because technical sounds good, cleanliness sounds good. So with this topic, the working group can be funded and the work can be started. And as you can see on the left side, the output of this working group was the first standard called VDA 19, volume 19. And this was published in early 2005. The first standards how to perform cleanliness analysis. And what you can see also on the left side, there's a drawing, and you can see all systems in car that are that have cleanliness requirements at the moment are in contact with a liquid in operation when the car is on the street, for example, with a fuel or with braking fluid or with cooling fluid. And the components in production are also in contact with liquids, for example, when machining with cooling lubricants or at the end in liquid-based washing processes. And because they are in contact with liquid in operation and in manufacturing, it makes sense to also test them with a liquid. That means it's a laboratory washing procedure to wash off the residual particles and then to collect them on a filter membrane and count them with an automated microscope. That was the idea of the procedures written down in VDA 19. In 2002, another working group started their work, and this was an international working group. And the output of this working group was the ISO 16232, a standard published in 2007. And although the first ISO 16232 consisted of 10 individual parts, that means 10 documents, which also have to be purchased individually, its content was already largely compatible with the VDI19. And that was a big advantage. And also the same people working on the VDI19 are working on the ISO and participated on this working group. And on the left side, you can see that the 10 different documents, the terms and definition, then 4 types of extraction methods, the agitation, pressure rinsing, ultrasound, and functional test bench. The same 4 principles also included in the VDI19. And regarding the analysis methods, gravimetry, microscopy, EDX, and liquid particle counters, these are also included in the VDI19. So it looks completely different, but from the content nearly the same. In 2006, the battery cells is not yet a major issue in the automotive industry, but there are already indications of sensitivities with regard to particles, because in 2006, laptop batteries from Sony self-ignited in at least 40 cases, so a lot of laptops burned down, and more than 100,000 laptops had to be recalled. And the cause of that were small metallic particles inside the battery, perforating some insulation layers, leading to internal shortcuts. And as a result of that, they start to burn those batteries. Also in 2006, a lot of experience came up because many companies produce components with cleanliness specification, have invested a lot of money in washing technology, industrial cleaning processes, have their own cleanliness laboratory, and regularly check the cleanliness of their components. But on the other hand, they often cannot comply with the required cleanliness. That means fulfill the cleanliness specifications. And therefore, they are looking for further levers to improve the cleanliness of their products. And sometimes they orientated towards solutions of other industry. They were looking about solutions from the semiconductor industry, from the medical device industry, from pharmaceutical industry, and therefore sometimes they shifted the conventional assemblies they have, for example, for gearboxes, into a clean room, as you can see in this picture on the right side. But nothing happened regarding cleanliness, because with a clean room, you can control very small particles in the micron or submicron range, but it doesn't help to control big metallic particles that are generated in processes like you see here in a screwing operation. That means they spend a lot of money without any effort regarding technical cleanliness. And due to that, a new industrial alliance was founded called MONSA. In German, it's Montagesauberkeit. In English, it's assembly cleanliness. And the output of that working group was the VDI19 Part 2, which was available since 2010. And this standard, or it's not a standard, it's more a guideline to help people, is called Technical Cleanliness in Assembly. And here we have 4 major chapters. One is the environment. And for example, here we established new concepts like a clean zone or a cleanliness room instead of a clean room. That means these new concepts are introduced in the automotive industry. Then in logistics, the next very important topic, the packaging of component is named as an important point of critical influences. The third topic, the personal. Here, people mention that particle emission from human beings is not that critical like in other branches, because the particles generated by a human being are not conductive, not hard, not abrasive. So people itself, persons itself, are not the critical factor, but the mindset of the workers and the motivation are key competencies working in, for example, a clean zone or cleanliness room. The assembly processes itself were identified as the main influencing factors It was very important to think about the entire process chain, not just to focus on, let me say, industrial cleaning techniques. And also in this VDI 19 part 2, the first description of dry sampling techniques were given, like particle traps, particle stamps, or suction systems. But here they were initially only for environment plants joining processes, not for the parts itself. The parts are checked with liquids, like described in VDI 19. And also topics that were not included were the cleanliness compliant development of parts and aggregates, the industrial cleaning technology itself, the formation of chips and burrs or their prevention, and not included is also the film contaminants. In 2011, something happens because from the European Commission, there was a restriction and lead and other heavy metals were forbidden in cars. Most people know that from lead-free soldering processes, but also the producers of bearing shells have to solve or change their technology because since the mid of 2011, all newly registered vehicles within the European Union must be equipped with lead-free bearing shells. What happened? In the past, these bearing shells that you can see here at the top right of this picture here are coated with a lead coating. And in the past, they were very robust regarding particles. Nothing happens. But the new coating systems that worked very well from the point of the bearing itself, but these new coating systems were very sensitive regarding particles, and we have a lot of breakdowns at OEM levels at their test benches for engines, because the entire engine broke down due to blocked bearings, because these bearing shells are built between the crankshaft and the engine block. And due to this sensitivity of these bearing shells with the new coatings, a lot of investment was necessary, because it's not just enough to clean these bearing shells. You have to clean each area of the engine that comes in contact with the oil that is transferred to the bearing shells. That means also you have to clean the crankshaft itself, and especially the inside oil borings of the crankshaft, and also the engine blocks where we have the oil channel, the main oil channel that brings or lubricate the bearings and bearing shells. That means you have to invest hundreds of thousands or millions of euro for high pressure water jet cleaning and deburring technology for these engine blocks. Roundabout after 10 years of technical cleanliness in 2011, if you have a look on the laboratories that are established, meanwhile, you can say roundabout 25 supplying laboratories were found all over Germany, and roundabout 1,000 automated light microscopes are sold until that time. That means also around about 1,000 labs are established in automotive industry or supplier industry, and also 50 automated scanning electron systems were sold at that time. So a wealth of experience with the VDI 19 has been gained. And with this experience of lots of laboratories and hundreds of people, revision of the VDI 19 was started in 2011 or between 2012 and 2014 in an industrial network called TEXA 2.0, Technical Cleanliness 2.0. And the aim of this revision, or the necessity to revise it, was people want to have a better comparability of their test results. There was a lack of comparability in the past. But on the other hand, they have the wish of more freedom regarding further tests. this was a problem, and this problem was solved in establishing different, let me say, pillars for these analyses that you can see here. And the left pillar here is the so-called standard analysis. Here we find technologies like the gravimetry or the light optical analysis. And these were regulated very strictly. The parameters like illumination and so on, or parameters of the image analysis were very strictly recommended. So here it's possible to have a very good comparability regarding the results. And if you want to know more about your particles, if you want to do root cause analysis also, so on, you can use methods of the further analysis that you can see here, or also if you want to make a monitoring with very fast technologies. But in these two topics, the further analysis and the abbreviated analysis, you're completely free what you're doing because these values are not discussed in customer-supplier relationship. If you want to talk about cleanliness specification, then please use these standard analysis. Also, in the new VDI 19 Part 1, you find information about for developers, how to develop cleanliness specification or a procedure for exceeding limiting values. You find information about health and safety requirements and a lot of case examples to support newbies in that field to make familiar with these technologies, and also the direct inspection that was included in the original VDI 19 was deleted because there was no technology available for a direct inspection that works in that time. In the meanwhile, not just, let me say, liquid-based systems are placed in car like engine or fuel engines or gearboxes with oil or cooling systems with liquid. We also have a big boom of the electronics. Just if you have a look on this part here, this part from 2012, in that time you have in a Mercedes E-Class 62 different control units. That means 62 PCBs all over these cars. So this was a real boom. And as you can imagine, electronics are very sensitive to particles, especially to conductive particles. As you can see here on the left side, this leads to shortcuts and malfunctions of these electronics. But if you have a look on the operation of electronics, this is in dry conditions, so they are not wet in the automotive. And also during the manufacturing processes, this is an absolutely dry environment. No liquids are used, and also electronics PCBs are not cleaned with liquid-based processes at the end of process chain. But when checking them in laboratory, at that time also liquid or solvent was used to clean them off. But the question is, are there other possibilities to extract particles from electronics from PCBs? And in that time also a new working group was established at the ZVEI, that's called, or this is Society for Electronic Producing Companies in Germany. And they established also a working group regarding technical cleanliness and established a guideline, which is now available in the second edition. And they took parts from the VDI 19 Part 1 and Part 2 and have a more precise look on typical aspects of electronic production and electronic parts to help people controlling their cleanliness, but also to show the limitations of cleanliness. And as you can see here, they also develop a risk assessment tool where people can assume or calculate the risk of shortcuts if you find some residual dirt particles, for example, on a PCB or inside a control unit. And from my point of view, this was a very targeted approach because they have a lot of discussion with specialists. They are doing their own research, their own developments. They have congresses to spread their knowledge, and they are also in dialogue with the OEMs to share their knowledge. And now we're coming to electromobility. That means, for example, from 2015 until today, the transition to electromobility and the first steps towards autonomous driving. And that means we have many new systems inside a vehicle, inside a car, that have their requirements for technical cleanliness. For example, we have electrical motors, we have high voltage power electronics, we have drive batteries, but not the battery itself, also the modules, or up to the big battery trays. We have fuel cells, for example, for heavy trucks, and not just the fuel cells, also the hydrogen supply systems with the tanks, the pipes, and the valves. And especially due to these autonomous driving here, we have a lot of cameras, we have sensors, we have optical scanning systems that come inside new cars. And that these new components are also leads to some challenges for testing in laboratory. Because we have sometimes very large components, especially the battery trays. Here we have parts with a length of 2 meters and a width of 1.5 meters, very heavy component, and it's not possible to handle them in a laboratory and to wash or clean them with a liquid or a solvent. Often we have dry processes chains, like I described at the PCB production. We have components under voltage, for example, the battery cells, and nobody wants to have a component under voltage in a liquid cleaning. In some applications, especially at the camera level, we have smaller particles, so we have to be more, or we need a more precise analysis, for example, with microscopes. And people want to have higher inspection scope and detection of damaging potential of particles. They want to get more information about the composition of particles and the real risk of particles. And we also have new solutions for these questions. For example, here is a new extraction system based on a suction system in combination with a brushing tool. And I think this is also well established in the market. I think we have 150 systems now in the market. And also the questions on the right side, declining characteristics, the blank value, which are very important parameters from the VDI19 part of view, and the comparability with other extraction methods are well known. And also there was a very good work of this ZVEE working group to get more information about the capability of these new extraction equipment. And also we have new approaches, as for example, using CO2, snow, as a blasting tool, a dry blasting tool to extract particles in a chamber. Chamber you can see here in the middle, and the jet of CO2 here at the right top picture. And also this technology can be used to extract particles from component in a dry manner. Regarding the procedure in laboratory, this is normally a manual performed procedure. You have a manual extraction that you can see here on the left side. You have a manual filter handling, drying, and at the end you have a fully automated analysis with normally light optical microscopes. But after these analyses, you also have to perform a manual double check. And in some, you have a lengthy inspection, you have small sample sizes, long reaction times, it's cost intensive and error prone. And people are asking for fully automated systems for checking cleanliness. And also in this topic or in this field, we have new approaches. As you can see here, now there are new systems on the markets where you have a sensor cell, where you have an integrated filtration and optical analysis in one measuring cell. That means you get the results immediately after extraction or while extraction, and these automated measuring cells can be combined, for example, also with a fully automated liquid extraction. So also a high potential for a future fully automated analysis of particles. Regarding the question of the damage potential of particles, people are interested, for example, in the hardness of particles, if they are abrasive, or the conductivity. And we have light optical analysis systems, fully automated, that provide a typification according fiber shape, metallic shine, and so on. And these are standardized in VDI19, but that's all. And other systems like a lip system that you can see here at the top, or especially this scanning electron microscopes with ADX systems that provide an elemental composition that allow a derivation of material classes that indicate the damage potential of particles. These are not standardized. And therefore, a working group was founded, I think, 1.5 years ago, to discuss these problems, because there are a lot of problems at the moment in customer-supplier relationship, because these results are not comparable. And the reason are insufficient definition of relevant method parameters. And this working group is working on a solution for that, also to find parameters to make these analyses more comparable, but independent from the system. So for different types of scanning electron microscopes, find a parameter set up to make them comparable. And today, electromobility is on the streets, on the road. And in some cases, we have big quality problems. For example, here you can see example from 2021. A vehicle catches fire while driving. And in addition, there was a door malfunction, and the driver can only free himself with difficulty. So people in automotive industry and quality departments are very, very sensitive to quality of their products, and also have a big focus on technical cleanliness. And now it's time to think about a revision of VDI19 Part 1 also. And this revision was requested by the VDA QMC itself in 2021. And here you can see the topic of a revision, for example, can be inclusion of the new extraction methods like this vacuuming or CO2 snow, or to make the SEM systems with the EDX analysis more comparable to uses also for standard analysis, and to also improve the fast systems like these optical filter blockage systems that I show you for automated analysis, to make it comparable with the light optical microscopic analysis, to use it also for standard analysis. And some other topics like measurement capability or standardized laboratory checklists, to expand the case studies to include some examples from electromobility, to re-include the direct inspection, because now we have some good solutions for different tasks or different questions in technical cleanliness. And last but not least, the measurement of low contrast particles. These all will be topics for the starting revision, and this is planned for the beginning of next year, maybe in January or February 2023, we will start this revision. So that's from my side. I hope you get some information, and I'm glad to answer your questions.
Thank you very much, Markus. It's really great to see how cleanliness analysis started and where it is going currently. So, dear audience, we are now about to start the Q&A session. If you have any questions for our speaker today, go ahead and type them in the Q&A box on the right-hand side. And while the first questions are coming in, I'd like to draw your attention also on the available handouts, which you find also on the right side of your screen. So feel free to download them for further material about technical cleanliness. And now let's start with the first question. I would suggest I just read them, and Markus, if you like, you can then answer them. So, how do you align the systems between supplier and customer? For instance, master filter.
Okay. Yeah. Normally, if you follow the parameters from VDI 19 part 1, I think it's not necessary because with these parameters, good comparability between light optical microscopic systems should be safeguarded. So from my point of view, it's not necessary to have a master filter if you follow these parameters. If you look on the entire procedure, starting with an extraction, filter handling, filter drying, and automatic analysis, I think it's more difficult because you have no, for example, master or standard for extraction of particles. So for the entire procedure, it's just possible to check single steps. For example, you can check the extraction by the qualification procedure, by declining curves, do a qualification. You can check if you can find or if you introduce particles, known particles inside an extraction system, if you find them afterwards. So if the extraction and the technology for that is good, you can check the microscope. But as I said, for the entire procedure, you can just check single steps, not the entire procedure.
Yeah. And part of the question is as well how to do a measurement system analysis study on the cleanness testing.
Yeah, I think that's exactly the same answering because for a MSA, you normally need some kind of a standard. For example, if you do a measurement of a size of part, of a diameter or something like that, you have a caliber, a known part. But as I told you, it's not possible to get a standardized contaminated part that you can use for such a MSA because you have hundreds or thousands of different components in automotive industry with their own production procedure, with their typical dirt. So it's not possible to have, for example, 1 or 2 or 5 standard contaminated parts doing an MSA. So you have to split the MSA to small parts and check these single parts, like the extraction, like the microscope, and so on.
Yeah. So for instance, exactly for the optical microscope, typically there is a particle standard that can be measured then.
Yeah. Exactly, but the particle standard normally it's related. Let me say to the dimension of particles and the number of particles. So normally they are black and white, and you can check the optics, the magnification, and so on. And the other parameters, for example, brightness, contrast, and so on, these are standardized by these standard analysis in VDI 19 Part 1.
Yeah. Okay. Yeah, thank you. So the next question is are there typical sizes of particles that are critical in battery applications?
It depends what you're looking on. If you're looking on the battery production itself, the front end, where you coat the metallic foils with the chemistry of the battery, I think here normally particles around about 10 or 20 microns can be critical, because here you have very thin isolation layers. And if you go into the back end, putting in these jelly rolls inside the can of the batteries, I think they're a little bit more robust. Let me say 100 or 200 microns. And then if you go to the modules or the big battery tray, then bigger particles are relevant. For example, due to the forbidden leakage of a big battery tray if it's in the in the car, because they must be very dense to prevent water inside. And herefore, I think it's bigger particles are relevant, up to 1 millimeter, for example.
Okay. And a question that's actually touching a similar point is, will plastic particles also become more important for cleanliness inspection?
Maybe, but not due to electromobility, because most particles that are critical there are conductive particles, like metals, for example, due to shortcuts. Maybe plastic particles are interested more in liquid systems for blocking of filters, or if you have small valves, for example, then also plastic particles might be critical. And of course, in optical systems, like a camera system or a scanning system for autonomous driving. Here, each type of particle is critical, because here, the optical blockage is the problem, not the density of a material or the hardness or the conductivity.
So let's say more or less particles on the camera, which are then disturbing the system.
Yeah, exactly. Especially if you have a bare die camera chip, because then it's possible to find the particles directly on the camera chip. And here you block them optical, which leads to a failure in the image.
Okay. And one question will be how to accomplish the ISO 16232 requirements for quality control extraction. Any CRM. I don't know if you can comment on this. Or...
No, sorry, I didn't get this question, and I'm not sure what CRM is.
Yeah, I know it actually as a customer relation management system. So, but maybe this is something that we will just contact the participant then separately and discuss it. It's no problem in the end. Certified reference. Okay, CRM is displayed as certified reference material. So,
okay.
For the ISO 16232, if there are, I would understand it if it's certified reference material.
Yeah, but reference material regarding what? Regarding a material analysis done by scanning electron microscope with EDX, or I'm not sure what is meant with these certified reference material, or it's related to the light microscope.
Let's see.
Sorry for that.
Yeah, maybe it's better to then have a personal exchange here. It's no problem. A question that just came in is as well how the particulate size is defined, for instance, for PCBs and PCAs, if there is a change as well or difference.
That's a very good question and also a very big discussion at the moment, because normally or in the past, the particle size for conductive particle is or it's the same like the pitch or the distance between the conducting paths on the PCB, especially on the integrated circuit level, or half the distance of the pitch. And this specification based on the pitch leads to very big problems in customer supplier relationships, because people see they always have bigger particles. For example, if they have a cleanliness specification of 200 micron conductive particle in a PCB and the housing, they mentioned that they have also 400 or sometimes 600 micron metallic particles inside these systems. But they also recognize that they have nearly no problems in the field inside the car. And that was, for example, the reason why the ZVEI in Germany developed this risk assessment tool to calculate if you have some amount of particles from or some particles, special sizes, larger than the pitch, how is the probability of a shortcut? And I think this tool is very often used in customer-supplier relationship to discuss cleanliness specification, but it's also used to develop cleanliness specification. So I think based on that, I think we will have a better base for discussion and also developing cleanliness specification. Because honestly speaking, it's not possible to have a die-cast aluminum part with no particle larger than 200 micron, or nobody can pay that.
Okay, thanks. So one question is as well, if the ISO 16232 will be updated at the same time as the VDA 19, and if you can estimate already a date for both updates then.
At the moment, I can just imagine a date for VDA 19 Part 1. We will start the revision beginning of next year, and I think around about 2 years we will work on that. So maybe in 2025, so in, let me say 2.5 or 3 years, I think the revision of VDA 19 is over and the new standard is available. And then we will see what happened. If there is a demand for revising the ISO 16232, we can do it like in the last revision. Then we will talk to other countries, to other working groups. We'll present what we worked out here in Germany, if it's interested for them, and if everybody agree on the progress or are interested in the progress we've done here in Germany, then we also can restart the international working group and revising also the ISO 16232.
Okay, thanks. And one other question is there any standard method to access technical cleanliness for in-house control, or should be always sent to external certified laboratories?
I think a lot of companies have their own cleanliness laboratories in-house, and they're performing this cleanliness analysis with the same methods like service supplying laboratories doing that. You need some kind of extraction equipment, filtration, and for example, automated light optical microscopic system, and then you can do it also in-house.
Yeah, I think exactly this is the point. So you can, we have several customers who did set up this in-house then as well, especially if the amount of samples is then quite high. It's beneficial in the end to do it in-house. You have more control in this. Of course, you need then an extraction method, so either a washing cabinet or the other methods that you described, and then this can be directly coupled with a microscope then for the optical analysis. So I see here a few questions, but I think it's better to contact the person separately to discuss it as well. So one question here maybe to the Z4E. So is the Z4E standard recognized by the VDA 19 or by the VDA? Maybe you can explain. I think it's not really a standard, so it's a guideline as well.
Yes, but I think some of the progress that is done in the Z4E standard will also include it in the new VDA 19.
Okay. Do you perhaps see a question where you say this is an interesting question that can be then discussed further in here?
Maybe this question, how far are we to have accurate material analysis from particles of 400 micron size?
Oh, yeah.
The question is, was this an accurate material analysis? I think if you have enough time and can do it manually, it's possible to do it with a scanning electron microscope and an EDX system. The discussed question at the moment is the fully automated scanning electron microscopic analysis, because with these systems you count size and make a material analysis of hundreds or thousands of particles on an analyzed filters automatically, and you just have time of, let me say, 1 second for each particle, and you don't get enough counts for a real precise analysis. So I think we get a better comparability of these systems after the revision of VDA 19 in 2 or 3 years. But if you want to have a real precise material analysis, then you have to do it manually. Or in a second step in a double check. So, for example, if you get the result from the automated analysis, and here you can see how we find metal particles of a composition of that, and then maybe you can recheck some of these or of the biggest particles manually. Especially, for example, if you are looking on Korund and aluminium, because here Korund is aluminium oxide, and let me say aluminium oxide you can find also as non-abrasive materials. So I think this will be difficult to find a solution for that, to have a precise measurement of abrasive particles, because they are very critical to some liquid-based systems, for example, in turbochargers, for the bearings of turbochargers and so on.
And I would say as well, for Korund, it's always good to have an optical inspection as well, not only the, let's say, scanning electron inspection, due to the, let's say, the lack of color in this, and the shape of the particle as well, I would say.
Yes.
And
fully agree to that.
What I would say here as well, a material analysis can then additionally be done if it's about a quick analysis then with a LIPS system that can be coupled with an optical microscope. So for instance, that this aluminum signal or aluminum material can be directly identified then, for instance, on particles, and to combine this directly to save some time and have a fast analysis on this. Okay. And then I do not see really further questions that are quite easy to discuss here. So for the other ones, we will contact you separately and speak to you. There's one coming in. And there's one question as well about that just came in for ferrous alloys, especially for then if LDX is not accurate enough to quantify elements like carbon, nitrogen oxide, if there is a further method to differentiate between these alloys.
Yeah, but I think this problem will not be saved by a fully automated analysis, and I fully agree to that you need then a manual metallographic analysis.
Yeah. Okay. Yeah. Okay, then thank you very much, the audience, for asking all these questions. And yeah, Markus, thank you very much for answering all these questions. And
you're welcome.
In case you have any further questions, just write us at info@leicamicrosystems.com, or you can of course visit us as well on www.leicamicrosystems.com. And in the next few days you will receive a link to this webinar so you can watch it on demand. And then once again, thank you all for joining the webinar and have a great day.